Hey everybody, and welcome to another edition of the Knowledge Graph Technology Showcase. This is a time-honored tradition that we do every December, and I've done over 50 of these. So if you don't see the vendor or the tool that you're looking for, make sure you check the playlist that I have linked down below. All right, and these are not promotional. I get no swag, I get no benefits from these vendors, I get no money from doing these. I do these so that I can get a feel for what's out there in the market because a lot of people ask me for my tool recommendations, but I also do it so that I can share my honest notes with you, and those are always at the end of the video. So make sure you check that out before you leave the video. All right, so today we're going to be looking at, that one. That's who we're going to be checking out today. So without further ado, let's go get started.
I'm Roy Lippmann. I am the co-founder and CDO of Falkor DB. So Falkor DB, although the company itself is quite new, we've been around for 2 years. The actual product had been in the workings for almost 9 years now, I would say.
Wow.
So the core product behind Falkor DB is an extremely fast property graph database, which under the hood uses sparse linear algebra and sparse matrices for both the graph representation, in-memory graph representation, but also we're utilizing those arithmetic constructs to both traverse the graph and run different graph algorithms on top of those. And the reason why we're doing all of that is purely for performance. So if there's one thing that we care about, it's performance. But there are some other really nice features. One of them, which really shines for the past, 2 years now, is the ability to run thousands of different graphs on a single database. So you have either a cluster or just a single instance of the database, but inside of it, you have fully disjoint graphs, as many as your system can handle. But this really, been a point of interest with the explosion of Gen AI and knowledge
Of
graph
course.
and people who want to keep a clear separation between their customers, saying each one of those customers have a different graph, so all sits nice and tight within a single database. So what we're seeing here is Falkor DB visualization or browser for our graphs. And the way that we've modeled this for this demo is that we have here 4 different types of entities. One represents users, then users can be connected to both folders or files, has permission in case the user has permission to a specific resource. And then we've also incorporated groups saying that users are part or belong to a group. And so we have some metadata, but I don't think that's really interesting for every type of entity. The thing is, if you're Google, then you have lots and lots of customers or different organizations who are managing their file systems with you. And you don't want to mix 2 different users on the same database or within the same graph. The pattern that we've seen is that for making this separation, the way that people are going about this is they're saying, oh, this is a user, but this user also belongs to Apple. So that's an Apple user, or that file belongs to Falkor DB. So I'm labeling it as a file, but I also need, for separation purposes, I need to add that extra label that keeps things separated. And this is where security comes in, because if you're making a mistake here, either by mislabeling or allowing one user to see entities that they're not supposed to, what you really want is to have a multi-graph architecture,
Mm-hmm.
meaning one database that handles the isolation internally. And so at the top here, the top left here, we have a drop down uh, which lists all of the graphs in your database. So I'm just gonna move through them and I'm just gonna pick another graph at random. So here's a different graph and let me run this. So here's a different graph. And so whenever I'm querying the database, I need to specify which graph do I want to communicate with.
Mm-hmm.
So we have permissions. Different users have different permissions to different graphs. So if you're set up your permission properly, then the isolation is maintained.
So then how is this different than, having subgraphs or named graphs? Because it's kind of the same thing. Like you have one giant graph, but it has subgraphs within it, and they don't always have to connect, right? But oftentimes they do, but you can still have permissions at the class level, at the domain level. Like there's different levels that you can add the permissions at. So how is this different?
The demo that we're seeing is running on a Falkor DB cluster.
Mm-hmm.
And within this cluster, we have three different nodes, machines,
Mm-hmm.
for that matter. If I run this command keys star, I'm gonna see here 1,332 different isolated
Mm-hmm.
graphs.
Mm-hmm. Mm-hmm.
Um, I mean, yes, you can manage all of the data in a single graph, but then we're running into scalability issues,
Mm-hmm.
you don't want that.
The other question I have is when you have it set up this way, do you ever find yourself having issues when you're trying to walk the graph because you've split everything up into sorry, not subgraphs, different graphs, where
Mhm.
maybe two graphs could actually connect together, but for one reason or another, they're in different graphs. Has that ever happened? Does that come up a lot?
This is extremely rare. I think that's a good point. I think that it could be very powerful to keep information separated on two different graphs, but every once in a while you do want to traverse from one graph to another.
Hmm. Hmm.
That is still possible if you're putting maybe a client application in the middle, but performance usually would go down
Hmm.
the drain because of this extra hop. Um, so
So you really need to know you need it before you do it.
yeah, well, I mean, uh, in the 9 years that I've been dealing with graphs, this had been raised. I mean, from what I've encountered, uh, very rarely, extremely rarely, on a different node in my cluster, the same command. So now on this different node, we have 1,228 different graphs. We have this benchmark that I've prepared. Um, Basically, it picks up some file at
Hmm.
random, the first one it encounters, and then it asks how many users are allowed access to this specific file.
Hmm.
And we are picking different graphs at random, and we're firing this query. So this is what I have here. This is the actual benchmark machine that I have. And just to verify the query that we're about to run. So yeah, this is the query that we've seen. Afterwards, I think it would be nice to see another query which simulates something similar to the list command where we're doing ls. Just give me the content of a folder. So the first run Yeah. Okay, these are all of the graphs in the database, and we are sustaining about 60,000 permission queries per second.
Wow. And so each of these is a graph, you said, right?
Each of these is a different graph.
So what kind of so are these are permission graphs though, right? Because I'm looking at these and most of these look like named entities. So these would be
No,
named
these
entities.
are these are fake names for companies. So here's
Oh, so each one
graph,
is a graph on a company. I see. I gotcha.
right? Yeah. All right. Oh, maybe we can run the other benchmark, which simulates the ls command. So I'm gonna switch from one query to another. So we pick a random user, the first one that we've matching, and then we ask to know for that particular user, a folder or all of the folders that he has permissions to.
Mm-hmm.
Then for each folder, we're asking which files are contained within it, and just give me the name of those
Mm-hmm.
files. So this is what we're about to run. So rerunning now with this different query. These are all of the graphs in our database. And similar to the previous one, we are able to sustain around 60,000 ls commands
Mm.
per second. And the nice thing about this architecture is that I can add more and more nodes to my cluster.
Mm-hmm.
So if I'm in a situation where I'm dealing with more data and I need more graphs, or the number of graphs remain, but I need a higher throughput. So let me add some extra machines. Let me distribute the graphs
Mm-hmm.
um, among a larger number of machines, and then I would have more compute power,
Yeah.
and so
Yeah.
I'm going to get more throughput. So I think this is one of the nice things, and I think that those who are dealing with data modeling that allows them to keep their graph separated can really enjoy scale out.
Yeah, I mean that's half the battle trying to get to that part. Right? Like the challenges of like even just thinking of some of the graphs that I've worked on. So when you are creating these views, right? You're calculating, pre-calculating on the graph. You are creating subgraphs, but it's still one giant graph. It's just you're only querying that part and
Yeah.
you're pre-computing it. It's so slow, and you have to do the pre-compute ahead of time. And then anytime the graph changes, you have to do it again and again and again and again. So it's not just I want it to be fast. It's well, all of that takes up a lot of time, a lot of effort, and a lot of money to do. So it sounds like what you've got going on here is going to help even in that aspect of things. It's more about the hard work and effort everyone will have to do to get to that point. If they're not there already. That's all.
Yeah, and I mean, sometimes the situation is that you're right. We don't have hundreds of graphs. We have one or two, which is I mean still fine. We still try to give you high performance
Yeah.
on a single graph. Once again, with all of this explosion of LLMs and AI, and I think I find this a little bit funny, is to use graphs to help with SQL queries.
Yeah.
Um,
Yeah.
and so we've got this use case from a number of different prospects who are basically managing a large catalog
Mhm.
of SQL tables.
Mm-hmm.
In the numbers are pretty much in the hundreds of tables. Each table have a whole bunch of different columns.
Mm-hmm.
And as many in the industry who were thinking about, yeah, just slap LLM on top of that and start having a conversation with your data. I mean, it's a nice spot, but it's more challenging
Yeah.
than it might sound like.
Mm-hmm.
Um, so basically, what people wanted is for the LLM to figure out, given a human composed question,
Mm-hmm.
what would be the SQL that I need to run in order to get the relevant answer or the relevant data.
Mm-hmm.
So if you have just a small catalog, that might be fine just to push the entire catalog into your LLM and let it figure out the SQL.
Mm-hmm.
It is becoming more and more challenging as your number of tables grows. And so what we did, and let me reshare my screen here, we're utilizing graphs once again to help with this text to SQL
Mm-hmm.
challenge. And so imagine a catalog of, let's say, 1,000 tables
Mm-hmm.
and all of the relationship between them via foreign keys. And so what we have here is such a catalog represented as a graph. We uh, we have here three different type of nodes. One which I think we can discard. The other two, one represents a table. So we have a table with its description. We're using embeddings. So Falkor DB comes with three different types of indices that you can utilize, all built in. You have the classical exact match or range index.
Mm-hmm.
You have full text indexing for prefix
Mm-hmm.
kind of search. And recently we've introduced vector search.
Mm-hmm.
And you can mix all of them together. And so this embedding that you see here is for semantic or vector searching.
Mm-hmm.
So this is a table entity, and the table entity is connected to its columns. And just like the table, a column has a name, it has its type, description, and embeddings. And we might be able, let me see if I can see if there's any type of connection between the different tables. Yes, okay, this is uh, a nice visual to see here. So tables are connected sometimes via some intermediate table,
Mm-hmm.
a mapping table. And so this is captured in the graph. So you might, not understand how can I go from one table to another. And the graph really helps with that because we're looking at this table, we're seeing that it has a column, and this column is a foreign key to a different table. And then we can use this foreign key relation to find a connection between two different tables. And this is a key feature within this text to SQL demo. And so the demo itself is available online. You can see it in under text-to-SQL.falkordb.com. It runs against this database. And so you can think about the catalog itself as a CRM catalog where you have all sorts of different table managing your CRM system. Let me just enlarge my font here. And so we have a number of prepared questions, but you can put in your own ones. So let's pick one. How many leads converted into deals over the last month? I think this is, a question that might be asked by someone within an organization who's not uh, well equipped with SQL skills,
Yeah. Yeah, it's a
or
lot of people. A lot of people are, they're business folks, and a lot of business folks might know SQL, but a lot of them don't.
right. And so let's run this. So let's quickly go over what happened here. So we have asked the question, how many leads converted into deals over the last month? This question was given to an LLM who knows about this graph and the way that it might be able to utilize it uh, to, at the end of the day, generate a SQL query. And so let's have a quick look at let me repeat the question and let's review the SQL. How many leads converted into deals over the last month? So select count distinct lc.dealID, okay, how many deal count as converted leads count from. All right, this is the first table. Lead conversions, LC. Now he's joining. Join deals on LC, lead conversion, sorry, LC.opportunity ID. Opportunity ID, okay, this seems right. Well, the lead conversion date is greater than the current date minus 1 month. So it seems about right. Here we have
And
a
is it, not to interrupt, but is it doing this just solely based on the graph that you've created? Because it also has to kind of understand what each of those things are. So is it also consulting the tables themselves to understand what that context is?
it so the way it goes about this is looking at this question and then running a semantic search, trying to figure out which tables and columns are most likely to be similar to that question.
Hmm.
So let's assume that the LLM, or sorry, the semantic search came out with this table might be relevant and that table might be relevant. But then he follows up with graph traversals in
Mm,
order to
sure.
figure out how can I go from this table to that table. But also I think that if the two tables are extremely separated apart, maybe the semantic search didn't get you the correct table. So I think that usually when you're asking a question, it is likely that the answer falls within tables who are closely related to one
Mm.
another. I think that if we look at the statistics, it's very highly likely that those tables are usually one or two mapping tables away from
Mm.
one another,
Well, this is
right?
also predicated on the fact that you have cleaned up data, or somewhat so, because if you don't, you have a bunch of tables that are old, outdated, duplicative. It's not going to give you the best. I mean, it's with any AI stuff, and graph for that matter. You have to be you have to be confident in your data before you can be confident in what it spits out. So I think that's just a
Right. I mean, I totally agree with that statement, and I think it's one of the ways that you can really improve subsystems is with this description field.
mm-hmm,
I
mm-hmm.
haven't really worked with SQL for a while, so I don't know how common is it to find descriptions on either tables or columns, but the nice thing about it, if you don't have these and you're lazy, you can actually ask an LLM to
Yep,
auto-generate
yep, yep, yep,
those,
yep. And it
right?
creates it on the fly because of the embeddings.